All right, so today we're taking a deep dive into something pretty wild.
Yeah,
The quantum theory of consciousness.
definitely a fascinating one.
It is. It really makes you think, like, what if our brains are actually using quantum mechanics to create consciousness?
Yeah, it really challenges our traditional view of the mind.
Absolutely. And the idea is that maybe it's not just neurons firing, but actual quantum processes happening in our brains.
Right?
And the big names in this theory are Roger Penrose, he's a physicist,
Mm-hmm.
and then you have Stuart who's an anesthesiologist.
Kind of an unexpected pairing, right?
Yeah, it's a pretty unique team up for sure. But their theory, it's called Orchestrated Objective Reduction, Orch or R for short.
Catchy.
It is catchy, right? And they believe that these quantum processes, they're actually what's going on in our brains to create consciousness.
That's a pretty bold claim.
It is bold. And it gets even weirder when you consider that one of the things they look at is how anesthesia,
The stuff that knocks us out.
exactly how that seems to mess with these quantum processes that they're talking about.
Yeah, that's a key piece of the puzzle for them.
It really is. So to understand their thinking, we need to start with these tiny structures inside our neurons called microtubules.
Most people think they're just kind of like scaffolding, holding the cell together, structural support.
Right, just kind of there.
But Penrose and Hamroff, they see them as way more important than that.
Okay, so what do they think these microtubules are doing then?
Well, they believe that microtubules are actually the key to these quantum processes happening in the brain.
Whoa, hold on. So you're telling me that these microscopic things, these microtubules, could be holding the secret to consciousness?
It might sound crazy, but that's exactly what they're proposing.
That's wild. So how does that even work? How do these microtubules create consciousness?
Well, they believe that microtubules are capable of something called quantum coherence.
And what is that quantum coherence?
That's a sustained quantum state.
Okay, so in simple terms, what does that mean?
Basically, they're saying that the brain could be acting like a quantum computer.
A quantum computer. Okay, now you're really losing me.
I know it sounds like science fiction, but let me try to explain it in a way that makes sense.
Please, because I'm drawing a blank here.
Okay, imagine you're flipping a coin. In a regular computer, it lands on either heads or tails, right?
Sure, heads or tails.
That's like your 0-1, the basic unit of information.
Gotcha.
But in a quantum computer, the coin is spinning in the air. It's both heads and tails at the same time.
Wait, how is that possible?
It's a concept called superposition. It's not until the coin lands and you look at it that it becomes one or the other.
Okay, I kind of get that, but how does that relate to our brains?
Well, Penrose and Hammeroff suggest that similar quantum processes could be happening within these microtubules in our neurons.
So instead of just zeros and ones, our brains could be working with a whole spectrum of possibilities all at once.
You got it. It's like our brains are tapping into this hidden level of complexity.
That's incredible. But if our brains are so warm and messy, how could these delicate quantum states even survive?
You've hit on one of the biggest criticisms of the theory.
I can imagine.
It's very difficult to achieve and maintain quantum coherence in a warm, wet environment like the brain.
Right, like a quantum computer has to be kept at super cold temperatures, close to absolute zero, to function properly.
Exactly. And our brains are nowhere near that cold.
So how could those fragile quantum states exist inside our heads?
That's the million-dollar question, and it's one that scientists are still trying to figure out.
So it's like trying to build a sandcastle in a hurricane. It just doesn't seem possible.
It's a great analogy, and that's why this theory is so controversial. But despite the challenges, it continues to intrigue scientists and make them think differently about consciousness.
I can see why. It's a real head-scratcher. So how do they even begin to explain how these states might collapse, leading to our actual conscious experience?
Well, that's where Penrose's idea of objective reduction comes in.
And this involves gravity, right? Like the force that keeps us on the ground.
You got it.
I'm not sure I see the connection there.
It's definitely abstract, but think of it like a wave approaching the shore.
Okay.
The wave represents the quantum state, spread out with all its possibilities. Then it hits the shore. That's the moment of objective reduction. The wave collapses, and all those possibilities become a single outcome.
So the wave is like the quantum state, and the shore is like reality.
It's a simplification, but you're on the right track.
Yeah.
Penrose suggests that in the brain, it's gravity's influence on these microtubules that causes this collapse.
Okay, so gravity is what's making these quantum states in our brains collapse. And that's what creates consciousness.
That's the basic idea.
It's a lot to take in, but I think I'm starting to get it. So these quantum states are constantly forming and collapsing in our brains because of gravity, and each collapse is like a tiny spark of consciousness.
That's a good way to visualize it.
It's mind-blowing.
It is, but it's important to remember that this aspect of the theory is highly speculative.
Speculative, sure, but definitely thought-provoking. But you mentioned earlier that anesthesia plays a role in this whole quantum consciousness thing.
Right.
How does that fit in?
Well, there was a study that found anesthetics, the drugs that make us unconscious during surgery, seem to directly affect those microtubules we were talking about.
So if anesthetics mess with microtubules, and Penrose and Hammeroff are saying that microtubules are essential for consciousness.
It seems to support their theory, right? The fact that something that directly affects our conscious state also impacts these very structures is quite a compelling piece of evidence.
It really is.
It suggests there might be a deeper connection there.
And then there was that other study, the one from Trinity College Dublin, that found evidence of actual quantum computation happening in the brain.
Oh yeah, that one's really interesting.
Yeah, what can you tell me about that?
Well, they were looking at this phenomenon called proton tunneling, which is a purely quantum process.
Okay, I have no idea what proton tunneling is.
It's a bit tricky to explain, but imagine you have a tiny ball in a wall.
Okay.
In classical physics, if the ball doesn't have enough energy to go over the wall, it just stops.
Right. Makes sense.
But in the quantum world, there's a chance that the ball can actually tunnel right through the wall, even without enough energy.
So it's like it's teleporting through the wall?
Kind of. It's a quantum quirk. And what's amazing is that they found evidence of this happening in the brain.
Whoa, seriously. So this quantum weirdness is going on right inside our heads.
It seems so.
And what's even crazier is that they think this might be connected to how we remember things and experience the world.
Yeah, they found this proton tunneling happening in brain structures related to short-term memory and conscious awareness.
So even basic things like memory could be tied to quantum processes.
That's what the research suggests.
Wow, that adds even more weight to the idea that consciousness itself might be a quantum phenomena.
It's a tantalizing possibility, isn't it?
It is. But I have to ask, with all this talk of quantum processes, there must be a lot of scientists who aren't buying into this Orch OR theory.
Oh, absolutely.
What are some of the biggest criticisms they have?
Well, as we've already touched on, one of the main criticisms is the issue of temperature and environment.
Right. We talked about that earlier. Quantum effects are super fragile, and our brains are not exactly the most pristine environment.
Not at all. Our brains are warm, messy, chaotic.
Yeah, it's hard to imagine these delicate quantum states surviving in that kind of environment.
Exactly. Critics argue that it's just too improbable. They point out that quantum computers need those extremely low temperatures, almost absolute zero, to function properly.
And our brains are nowhere near that cold.
Nope, not even close. So they say that the brain is just too hostile an environment for quantum mechanics to be playing a significant role.
So they're basically saying that the brain is too chaotic for quantum mechanics to be driving consciousness.
Pretty much.
I can see their point. It's a pretty tough argument to counter.
It is. But despite the skepticism, the idea that consciousness might be a quantum phenomenon continues to fascinate researchers and push the boundaries of our understanding of the mind.
This is definitely a rabbit hole I'm happy to go down. But even if this theory is never fully proven, it's still incredibly thought-provoking, isn't it?
Absolutely. It forces us to ask these profound questions about the nature of consciousness and reality itself.
It makes you wonder, what if consciousness is more than just a product of the brain? What if it's something fundamental to the universe?
Those are big questions.
They are, and they're questions we'll be exploring next time as we continue our deep dive into quantum consciousness.
It's going to be a mind-bending journey, so buckle up.
I can't wait, and I hope you can't either.
Okay, so last time we kind of left off talking about this idea that gravity might be playing a role in consciousness.
It's a wild concept.
Yeah, it is pretty out there.
So can we unpack that a little bit more? How do Penrose and Hammeroff actually see this working?
Well, to understand that, we got to go back to those microtubules.
Right, those tiny structures inside neurons.
Exactly. They're at the heart of this whole theory.
Okay, so remind me again, what's so special about these microtubules? Why are they so important for consciousness?
Penrose and Hammeroff, they think that these microtubules are actually capable of quantum computation.
Wait, so they're like tiny quantum computers inside our brains?
That's the idea. They believe that within these microtubules, you have these delicate quantum states forming.
Quantum states, like the kind they use in quantum computers.
Exactly. And those quantum states, They exist in superposition.
Superposition. That sounds familiar.
Remember we talked about that with the coin flip. It's the idea that something can be in multiple states at the same time until it's measured or observed.
Right, right. Like the coin spinning in the air. It's both heads and tails at the same time until it lands.
Precisely. And in the case of consciousness, they believe it's this moment of objective reduction that causes these quantum states to collapse and give rise to our conscious experience.
Okay, back up for a sec. Objective reduction. What exactly is that?
It's Penrose's proposal that gravity plays a role in the collapse of these quantum states.
Gravity. I'm still struggling to wrap my head around that.
It is a big leap. You see, in quantum mechanics, when you measure something, you collapse its wave function, forcing it to choose a definite state.
Okay, so gravity is kind of like making that measurement.
In a way, yes. Penrose argues that in the brain, it's gravity's influence on these microtubules that triggers this collapse, leading to moments of conscious awareness.
I mean, it's a fascinating idea, but how do these quantum states even survive in the first place? Isn't the brain kind of a hostile environment for them?
You're hitting on one of the biggest challenges to this theory. You're right, quantum coherence is easily disrupted by external factors.
Like the warmth and all the electrical activity in the brain.
Exactly. It's incredibly difficult to maintain those delicate quantum states in such a noisy environment.
So how do Penrose and Hameroff explain that?
They argue that the structure of microtubules might actually provide a sort of shielded environment where these quantum states can exist for a bit longer.
So the microtubules are kind of protecting the quantum states from all the chaos in the brain.
That's the idea. They point to the geometric arrangement of these microtubules, saying that it could create a kind of protective cage for these quantum processes to happen.
Interesting, but it still feels like a long shot to me.
It definitely is a controversial idea. But let's switch gears for a minute and talk about that study on anesthesia.
The one that found it affects microtubules.
Yeah, that one. It actually gets even more specific than that. They found that anesthetics don't just affect any part of the microtubule. They seem to target these regions called hydrophobic pockets.
Hydrophobic pockets. What are those?
Well, simply put, these pockets are areas within the microtubule protein that repel water.
Okay, and why is that important?
Well, anesthetics also happen to be hydrophobic, meaning they repel water too. So they seem to bind to these specific pockets in the microtubules.
So the anesthetics are latching onto those hydrophobic pockets, and that's what disrupts the quantum processes.
That's the hypothesis. It's like they're jamming the quantum machinery within these microtubules.
And that's what leads to unconsciousness.
Exactly. It's a pretty compelling piece of the puzzle, right?
Yeah, it's starting to make more sense now how all these pieces fit together. But we can't forget about that other study we mentioned earlier, the one from Trinity College, Dublin.
Oh yeah, the one about proton tunneling.
That's the one. You remind me what they found again?
Well, they were studying this phenomenon called proton tunneling, which is like a purely quantum process.
Quantum tunneling. Okay, now we're getting back into the realm of things I don't understand.
It's a bit mind-boggling, but imagine you have this tiny ball, right? And there's a wall in front of it.
Okay.
In classical physics, if the ball doesn't have enough energy to go over the wall, it just stops, right?
Yeah, that's how normal physics works.
But in the quantum world, there's this chance that the ball can actually tunnel right through the wall, even without enough energy. It's like it disappears on one side and reappears on the other.
That sounds impossible. How can something go through a wall without enough energy?
That's the magic of quantum mechanics.
Yeah.
And that's proton tunneling in a nutshell. What's fascinating is that they found evidence of this happening in the brain.
Whoa, seriously. So this quantum tunneling thing is happening right inside our heads.
Apparently so. And here's the kicker. They found it happening in brain structures that are involved in short-term memory and conscious awareness.
Wait, so you're telling me that quantum tunneling might be connected to how we remember things and experience the world?
It's a possibility. The researchers suggest that this proton tunneling could be what allows for the rapid and efficient transfer of information in the brain, which is essential for consciousness.
So it's like these quantum processes are giving our brains an extra boost, making them work faster and more efficiently?
It's a fascinating idea, isn't it?
Yeah.
It challenges our traditional view of how the brain works.
It does. So we have microtubules, quantum coherence, objective reduction, anesthetics, messing with hydrophobic pockets, and now proton tunneling. It's a lot to take in.
It is a lot.
But I have to ask, with all this evidence pointing towards quantum processes in the brain, why are so many scientists still skeptical of this theory?
That's a great question, and it's important to acknowledge those criticisms because there are some valid concerns.
What are some of the main things they point to?
Well, the biggest sticking point, as we've mentioned a couple of times, is the issue of temperature and environment. Quantum effects are incredibly sensitive to their surroundings.
Right, like quantum computers need to be kept at those super low temperatures.
Exactly. And our brains are warm and messy, far from the ideal conditions for quantum processes to thrive.
So the critics are saying that basically the brain is just too chaotic for those delicate quantum states to last long enough to be important for consciousness.
Yeah, that's their main argument. They think the brain is too hot, too noisy, too much going on for quantum mechanics to be playing a starring role.
Okay, I see their point, but how do Penrose and Hameroff respond to that criticism?
Well, they argue that, while it's true the brain is a challenging environment, the structure of microtubules could offer some protection for these quantum states.
So they're saying that those microtubules are like tiny fortresses shielding those quantum processes from the chaos of the brain.
That's a good way to put it. They suggest that the specific arrangement of molecules within microtubules could create a sort of quantum shield.
Interesting. But even with that shield, I imagine it's still hard to prove that these quantum states can actually stick around long enough to matter.
Absolutely. That's one of the main criticisms. We just don't have definitive proof yet that these quantum states can last long enough to be relevant for consciousness.
So what would it take to prove it? What kind of evidence would convince the skeptics?
Well, one of the big things would be developing new technologies that can actually directly measure those quantum processes happening inside a living brain.
So we need to build instruments that can basically see into the quantum world of the brain.
Exactly. And that's not easy. But there are scientists working on it right now. They're developing things like quantum probes and sensors that could potentially detect those delicate quantum states.
That's incredible. It would be like opening a whole new window into how the brain works.
It would be a game changer for sure.
But in the meantime, while we're waiting for that technology, we can't ignore the other theories out there that try to explain consciousness without resorting to quantum mechanics.
Right, there are other contenders in the ring.
Exactly. Can we talk about some of those alternative explanations for consciousness? Like, how do they differ from the quantum approach?
Of course. So let's start with integrated information theory, or IIT for short.
Okay, what's that one all about?
Well, this theory basically proposes that consciousness arises from the complexity and interconnectedness of information within a system.
So the more complex the system and the more interconnected the information is, the more conscious it is.
Exactly. It's all about the richness and integration of information.
So a brain, with all its billions of neurons firing and communicating, that would have a high level of consciousness.
Right, but here's the interesting thing. IIT doesn't limit consciousness to just brains.
Really?
Oh.
So what else could be conscious, according to this theory?
Well, it suggests that any system that exhibits a high degree of information integration could have some level of consciousness, whether it's a computer, a network, even the universe itself.
Whoa, that's a pretty radical concept.
It is, and it's a point of much debate.
Okay, what about the other theory you mentioned? The global neuronal workspace theory.
Ah, yes, that one's a bit different.
How so?
Global neuronal workspace theory proposes that consciousness emerges when information is broadcast globally throughout the brain.
So it's like a global announcement system in the brain.
That's a great analogy.
Yeah.
So the idea is that when information is widely available across different brain regions, that's what makes it conscious.
And that allows for the integration of all those different senses and memories and emotions that make up our conscious experience.
Exactly. It's about information sharing on a grand scale.
So we have quantum consciousness on one side and then these other, more classical theories on the other.
It's a real battle of ideas.
It is. So with all these different theories vying for the title of best explanation for consciousness, where do we even go from here? Which one is right?
That's the million-dollar question, isn't it? And to be honest, we don't really know yet. Each theory has its pros and cons, and the debate is probably going to continue for a long time.
I'm on the edge of my seat waiting to see how it all unfolds. But even if we never find a definitive answer, just exploring these ideas is already so mind-expanding, isn't it?
I completely agree. Even if none of these theories fully capture the mystery of consciousness, they still force us to confront some really profound questions about the nature of reality.
They make us think outside the box, consider possibilities we might never have thought of before.
And that's the beauty of science, isn't it? It's a journey of exploration, always pushing the boundaries of what we know and what we think is possible.
Well said. So, to our listeners out there, keep an open mind and don't be afraid to dive into these complex and sometimes confusing ideas. The search for an explanation for consciousness is a thrilling adventure, and who knows, maybe you'll be the one to uncover the missing piece of the puzzle. All right, so we've dug into the science, the theories, the evidence, even some of the criticisms.
It's been quite the journey.
It really has, but now I think it's time for the fun part.
Oh, and what's that?
The what if?
Like where this is going.
What if this whole quantum consciousness thing is right? What if our minds are actually connected to the universe in this crazy quantum way? What happens then? How does that change our understanding of, well, everything?
Those are the big questions, aren't they? And exploring those what-ifs can lead to some really profound insights, even if the theory itself turns out to be wrong.
So let's get into it. What kind of quantum reality are we talking about here? If consciousness is really a fundamental part of the universe, how does that change how we see ourselves, our place in the cosmos, the whole shebang?
Well, for starters, it suggests a level of interconnectedness that's pretty mind-blowing.
Right, we touched on this earlier, the idea that we're all connected, but now we're talking about it on a whole other level.
Exactly. It's not just some feel-good spiritual concept. It's a fundamental aspect of reality.
So instead of consciousness arising from the brain, it's more like the brain is tapping into this universal consciousness that already exists.
That's one way to look at it.
Wow, that's a huge paradigm shift. So we're not just these isolated beings, we're all part of this interconnected web of consciousness. That's a beautiful thought.
It is. And it raises some really fascinating questions, like, what are the implications of this interconnectedness? Could we somehow tap into it, communicate with each other, or even other beings through this quantum web?
Okay, now we're getting into science fiction territory, but I'm here for it.
It's fun to speculate.
It is. So you're saying that there could be other conscious beings out there, and we could potentially communicate with them through quantum entanglement.
It's a possibility that some physicists take seriously.
That would change everything. Forget radio signals, we'd be looking for entangled minds.
It would definitely open up a whole new way of thinking about extraterrestrial life, wouldn't it?
Absolutely. But let's bring it back down to Earth for a minute. We've talked about the potential implications for things like mental health and neuroscience, but I'd love to explore those in more detail.
Sure, let's dive in.
So, mental health. How could understanding the quantum nature of consciousness revolutionize how we treat conditions like depression, anxiety, even schizophrenia?
Well, the current treatments for these conditions, they often focus on managing the symptoms.
Right, like medication or therapy.
Exactly. But if we can pinpoint the specific quantum processes that are disrupted in these conditions, we might be able to develop treatments that target the underlying cause, not just the symptoms.
So instead of just masking the problem, we could actually be fixing it at the quantum level.
That's the idea. Imagine therapies that work by harmonizing quantum states in the brain or restoring disrupted quantum coherence. It would be a whole new approach to mental health.
It would be revolutionary. And what about the broader field of neuroscience? How would this change how we study and understand the brain?
It would be a complete paradigm shift.
I can imagine. Right now, neuroscience is all about neurons and synapses and electrical signals.
Yeah, it's very much rooted in classical physics and chemistry.
But if quantum processes are at play, we'd need to incorporate quantum mechanics into our models and our research methods.
Exactly. We'd need to develop new tools and techniques to study the brain at the quantum level.
It would be like unlocking a whole new dimension of the brain.
And who knows what amazing discoveries await us there. It could transform our understanding of everything from memory to decision-making to creativity.
It's so exciting to think about all the possibilities. But of course, we can't talk about quantum consciousness without addressing the elephant in the room, artificial intelligence.
Ah, yes, the question of whether we can create conscious machines.
That's the one. I mean, if consciousness is really based on quantum mechanics, could we someday build machines that are not just intelligent, but actually conscious, aware, sentient?
It's a question that's both exhilarating and terrifying at the same time.
I know, right? It's like straight out of science fiction.
But it's a possibility we need to take seriously. If we do manage to crack the code of quantum consciousness, the implications for AI would be profound.
I can only imagine. Conscious machines could revolutionize so many aspects of our lives, but it also raises so many ethical questions.
Absolutely. We need to be incredibly careful about how we develop and use this technology. We need to define what it means for a machine to be conscious, what rights it would have, how we would ensure its ethical treatment.
It's a huge responsibility, and one that we can't afford to take lightly.
We need to start having these conversations now, before the technology outpaces our ethical understanding.
You're absolutely right. This is not something we can just brush aside. But even if we never create conscious machines, just the act of exploring the quantum nature of our own consciousness can have a profound impact on how we see ourselves and the world.
It forces us to confront the big questions. Who are we? What is the nature of reality? What is our place in the universe?
And those are questions worth pondering, even if we never find definitive answers.
Exactly. The journey itself is just as important as the destination.
I couldn't agree more. This has been an incredible deep dive into the world of quantum consciousness. We've explored the theories, the evidence, the criticisms, and the mind-blowing implications. It's a topic that's sure to keep scientists, philosophers, and anyone with a curious mind busy for years to come.
It's a fascinating field, that's for sure. And who knows what groundbreaking discoveries await us just around the corner.
One thing's for certain, the quest to understand consciousness, whether it's through the lens of quantum mechanics or any other theory, is one of the most important and exciting scientific endeavors of our time.
It's a journey that's worth taking, even if the destination remains shrouded in mystery.
Well said. And to our listeners, thanks for joining us on this incredible adventure. We hope this deep dive has sparked your curiosity and left you with more questions than answers. Keep exploring, keep questioning, and never stop marveling at the wonders of the universe and the mysteries of your own mind.